I guess now I'll introduce our speaker, Jim Gates. He doesn't really need an introduction from members of the BTPC. He is our fearless leader, but he has a long history in high energy physics, supersymmetry, string theory, and he's also the current chairman of the APS Physics Society, American Physics Society. So without further ado, I leave the floor to Jim to present on his talk, How Can Supersymmetry Show Up in a Mineral?
Thank you, Stephen. It's my pleasure actually to be the inaugural speaker. And when I saw the announcement of the IDEA seminar series, I said, you know, we should make this a little bit edgy, have it out on the edge where it's not quite comfortable and talk about some crazy, crazy things that might be unlikely, but who knows? We live in a universe that's really interesting and unlikely things seem to happen regularly. So with that title, I was actually inspired to give this talk about some research which is actually underway, and let's get started. Don't want to waste any time here. So let me see if I can bring this up. And I seem to be having a bit of, hang on just a second here. Okay, is everyone seeing my slides now? Very good. So can SUSY show up in a mineral? A very strange question, but by the end of this talk, I hope to convince you that it's not as strange as you might think. So this starts back in 2004. I wrote this paper with Michael Fox, and there are problems in supersymmetrical theories that have not been solved to this very day, even though the subject is almost 50 years old. And so in 2005 and 2004, Michael Fox and I started having an interesting sort of discussion, and I'm going to paraphrase it because this isn't literally true, but the question becomes, if you're trying to study something as complicated as the supergravity limit of M theory, is there a way to explore this theory, not directly, but instead by thinking about a kind of shadow that it could cast into a one-dimensional world? In other words, we're looking for like projections of the full field theory, and we want to find out how much, essentially the first question is, how much information could you retain by looking at such a projection? So thematically, this figure captures it. You imagine that there is something like M theory, which is like the sun, and it casts its a ray of light through supergravity 11 dimensions, and you try to catch that ray of light by looking at supersymmetrical quantum mechanics in one dimension. So let me start with supersymmetry, because I'm not sure how familiar people are with the idea. I know it's been around for almost 50 years, but I like to summarize it in a very simple manner. So what is supersymmetry? Well, first of all, we imagine that there exists an operator that has something to do with the equations of nature, and we call this the supercovariant derivative. It satisfies an algebraic relationship that you can see written on this line, and the closure is onto the four space-time derivatives of time and the three directions of space. The coefficients of the closure are the famous Dirac gamma matrices, as in the Dirac equation. And so first of all, you have to imagine that such a mathematical operator exists. And then the other thing that you need is some Lagrangian that describes the physics. Now, for those of us who are particle physicists, this Lagrangian that we have in mind is actually the Lagrangian of the Standard Model. That is the things that, the expression that contains kinetic energies for the force carriers, the kinetic energies for the particle fields, as well as their interactions. So you imagine there's a Lagrangian for some system of interest, and this abstract operator that you're looking for that satisfies this equation has to satisfy an identity that if this operator is applied to the Lagrangian, the answer is a total derivative in terms of this object we call the supercurrent. So that's the simplest definition of supersymmetry that I can give you. So let's see if we can find some Lagrangians that satisfy these attributes. And in fact, we're going to find a zoo of these things. So let's plunge into the zoo. Well, here are three such Lagrangians. The Lagrangian of the first is called the chiral supermultiplet. That's the CS over here. It consists of a scalar field A, a pseudoscalar field B, a fermion, but this is actually a Majorana fermion, not the usual Dirac type of fermion, and then two other fields. And you'll notice that no derivatives of these F and G's occur, which mean if you use the Euler-Lagrange equation, you get an algebraic result. You don't get a propagating equation. So no physical degrees are carried by F and G. In a similar manner, if we look at this equation, D has that character. It doesn't appear any place in the Lagrangian with derivatives, and therefore Euler-Lagrange equation tells us that this will be purely algebraic. These sorts of degrees of freedom are called auxiliary fields. And the problem that I was telling you that has never been solved in supersymmetry is if you go up to 11 dimensions, which we're told is the limit of M theory, we know the fields that play the role of the gauge field in 11 dimensions. This is replaced by the graviton and a gauge 3 form. This field is replaced by the gravitino in 11 dimensions, but we don't know anything about these kinds of fields in 11 dimensions. In fact, for most interesting supersymmetry theories, we don't know what constitutes this continuation. Now you might wonder, how can you study physics? Well, since the equations of these objects are algebraic, all the propagating degrees of freedom are carried by things like this. And so essentially, all of the study of supersymmetry is what is technically known as on-shell supersymmetry. Namely, you're studying supersymmetry when the equations of motion of the fields are satisfied. Well, suppose you do something like string theory. Well, if you stop and think about it, if this string has an effective action, those equations of motion are likely to be different from the free equations. And so if you have these interactions, they are probing the structure of these unknown auxiliary fields. And so that's the kind of problem that I'm very interested in. I first met this problem in 1977. I was a postdoc at Harvard, and John Schwartz had invited me to come out to Caltech because we thought that we were going to be able to solve this problem for a very famous theory called N=4 super Yang-Mills theory. I went out there, I was out there for about 6 weeks, we failed. And in fact, this problem has never been solved in the 40-something years since then. In fact, a lot of people think it cannot be solved. They have so-called no-go theorems. But one of the things that I find really interesting about physicists' no-go theorems is that often they turn out to be where-to-go theorems. Namely, they sort of tell you what assumption in deriving the no-go theorem should I relax to get the result that I want. And so I've been chasing this problem off and on since my days as a postdoc, and this talk is really around that part of my activities as a physicist. So, wow, this is the multiplet that we just talked about, the so-called chiral multiplet. This, as a Majorana particle, is sort of, I like to tell audiences that are less technically astute than this one that this is like half an electron, because you know the Dirac field is a complex field, whereas this thing is actually a real field. These are the so-called selectrons. So for every Majorana piece of a spin 1/2 field, there's a scalar and a pseudoscalar. So if you had a Dirac field here, there would be 2 scalars and 2 pseudoscalars, and those are the selectrons. And those are the sorts of things that people who look at beyond the standard model physics are trying to figure out, is this going to influence the kind of experiments that are observable at CERN? Here we have the vector supermultiplet with my cursor circling the photon field. Again, in order to have this supercharge and supersymmetry, there has to be a super partner to the photon. It's called the photino. And again, if you know the Lagrangian, you can actually sort of calculate, make good guesses for how these other particles are going to be there. And that's what's going on at CERN. People have made some appropriate sorts of assumptions. They have written down Lagrangians. They have derived cross sections from those Lagrangians. They set up templates for the influence of these extra things. And then they're going and looking for these influences at the experiments that are underway at the LHC. Before 2006, most physicists I know thought it would be very simple to find supersymmetry. I was not among them. In fact, in 2006 or so, I wrote a paper entitled, Is String Theory Phenomenologically Viable? And in this paper, I expressed my great skepticism that we would find supersymmetry in the first scientific run. That first run came and went. There was no supersymmetry. And we finished the second scientific run. I've not heard of any evidence that supersymmetry has been detected. And so for a lot of the community, there's starting to be a sentiment that, well, supersymmetry is dead. The only problem with that sentiment is that supersymmetry is actually not a model. It's a frame, it's a framework. And so, you know, it's just like when you learn Newton's second law, if you learn how to describe a falling particle and someone gives you a mass spring system and it doesn't obey the equations that you thought, you don't get upset. You say, oh, I'm using the wrong set of equations in the context of Newton's law. And so that's what's actually happened so far with the LHC, is that all of our, what we thought might be equations simply have not been verified by nature. Let me stop here to talk about Hodges duality, because I showed you three Lagrangians, but actually there are many, many more. There are a total of 10 minimal representations. And the way to understand the prolific number of these is to first discuss a property called Hodges duality. So let me take a scalar field, call it phi. If I take its derivative, I'll call that f sub a. I use underlined letters like most people use Greek letters. So this is a 4-vector index for me. So here's a scalar field. I'm taking its first derivative. Because of this definition, none of you would be surprised to write this equation. I'm going to call this a Bianchi identity, right? I mean, it's a triviality. The fact that f is the derivative of something says this is satisfied. On the other hand, if you take the Lagrangian of motion, and I'm only talking about the massless scalar field, and look at its equation of motion, you can actually write it in terms of f, and this is the form of it. Now let me talk about an entirely different field. Let me introduce a second-rank skew-symmetric tensor field. I'll call it B. I'll act on it with a derivative, and then I'll contract that with an epsilon tensor. I get an object I call H. Well, it turns out that you can write a Lagrangian in terms of this, and here is that Lagrangian. And the normalization I might be off, but I'm not worried about normalizations right now. Now, what's really interesting about H is because of this epsilon tensor, it satisfies this equation. On the other hand, if you were to vary this Lagrangian with respect to V, you would find out the equations of motion look like this. And now, if you stop and look, you say, wait a minute, this looks exactly like that, and this looks exactly like that. And so these two theories are dual to each other. Now, by using duality, I can get to a lot of other supersymmetric multiplets. So let's see how we can do that. But before I leave duality, there's one other point, namely, if I was describing Maxwell theory, I would have a photon field. I would calculate its Maxwell field strength, and then I would write the Lagrangian as I've shown here. The equations of motion for the Lagrangian, since there are no other sources, is the free Maxwell equation. On the other hand, because of the definition of F, the Bianchi identities can be concisely written as a Levi-Civita tensor times a partial derivative on F. So these two sets of equations at the bottoms are what we normally call the source-free Maxwell equations. And if we were to make a transformation replacing F by epsilon times F, which I have shown you at the lower part of the screen, what you would find is that the equation of motion for the, in terms of the A tilde field, would switch and become the Bianchi identity, and the Bianchi identity would become the equation of motion. In other words, taking the dual of a spin 1 theory leads back to a spin 1 theory, whereas taking the dual of the scalar field led to a gauge 2 form. I can apply this idea back to my supermultiplets. Let's go backwards for a moment. So here are our Lagrangians that we started from. Let me take the dual to this object. The dual to a scalar we found was a gauge 2 form, but that's exactly what happens here. So this theory and this theory are related by taking Hodges duality on one of the spin 0 fields. You can think of phi as just being the field that was not treated. So if we apply this idea to all of the fields, we find a zoo. Here's the usual chiral multiplet. Here's one where I have taken a duality transformation for one of the auxiliary fields. Here's where I've taken it for this other auxiliary field. And here's where I've taken it for both auxiliary fields. So there are actually 4 different versions of the chiral multiplet in terms of representation theory. It's not a single theory. What about for the vector multiplet? Well, we already talked about duality on a vector, and you'll notice I've switched to Latin letters here for space-time indices, but I beg your indulgence that I switch back and forth. We've already talked about the fact that a spin 1 field leads to another spin 1 field under duality. So applying duality to this doesn't get us something new. But what about to this field here, this D field? Well, it turns out you can apply a duality transformation to it, and you are led, I'm sorry, first of all, I can consider a vector or an axial vector. So that's obviously a change, but I could do a duality transformation. And I find that this so-called auxiliary field gets replaced again, this time by a 3 form. And I could do that for the other multiplet. So there are actually 4 different vector multiplets. And then finally, we can talk about the tensor multiplet. This tensor supermultiplet actually shows up in the theories of supergravity and string theory. It's somehow related to gravity in those theories. We can do an axial transformation. And so the phi in this standard tensor multiplet becomes is a scalar. Under axial transformation, it becomes a pseudoscalar, but nothing else happens. So now we know about the zoo. There are 10 such particles that are 10 such particle systems, sets of equations that constitute the minimal representation of supersymmetry in 4 dimensions. So can we try to tame this madness? Well, one thing that we can do to try to find a simpler version of these theories is use the light cone as given to us by Albert Einstein. Instead of trying to solve, typically when we physicists are trying to solve a problem, we imagine that perhaps we're given some data and we're going to propagate it to the entire light cone in the future. On the other hand, the problems that I and John Schwartz nor anybody else in the world have solved have beaten us. We don't know how to do this. So a simpler problem is to look at the analog, but only along a line that points within the future cone, not in the entire future cone. And so that question that Michael Fox and I were asking is really, if you give me some data here at the origin and I propagate into the future trying to maintain supersymmetry, how good am I at actually doing that? And because all such lines in the future light cone can be brought to lie along the time axis, and essentially you can just say, I'm going to work in supersymmetric quantum mechanics, where time is the only variable. So here are our, I'm going to pull one other trick I need to explain to you. Remember I showed you that there were these dualities that take my zoo and turn one system into another. I can apply that just between the standard chiral multiplet and its double dualized version, which I have here at the bottom. In a moment, well, you'll see why I'm doing this. But let me, instead of working directly with this, work with the bottom set of equations. Wow, diagrams. It turns out that if we go back and look at those equations, these are full 4-dimensional equations. You can see the partial derivatives have an index with points in 4 directions. But if I were to reduce this theory to say all the variables only depend on time, then the only derivatives that would occur here would be temporal derivatives. And if you look at the structure of the equations here, well, here's the time derivative. What you'll notice is that if we look at the supercharge on a fermion, it always goes into time derivatives of bosons for the propagating fields. But by working with the dualized variables, that's also true for the auxiliary fields. And furthermore, if you look at the supercharges on the propagating fields, they go into something that's proportional to the spinner. If you work in terms of the dualized fields, once again, you find that they go into something proportional to the spinner. So it's making the role of auxiliary and propagating fields more similar than it is when you work with the standard formulation. And that we found to be convenient to try to understand the systems that we're studying. And in fact, what I'm showing you here are a set of figures, we call them adinkras, and there are a set of Feynman rules associated with these objects. And if I impose those Feynman rules on these objects, I get back these equations in the limit where only temporal dependence is occurring. So these equations are somehow encoding the information that we see here in terms of gamma matrices and what have you. That information is now encoded in the links of these diagrams. Well, let's go to the vector multiplet.
So sorry,
yes,
Jim. So are can you just briefly mention what the colors represent in the
yes,
diagrams?
thank you very much. Thank you very much, Stephen. Stephen. So if you go back to the equations, you'll notice that this object has an index A. This index A takes on 4 values. So in fact, there are 4 independent supercharges. And so when we do it diagrammatically, we use color to represent the orbits under the 4 supercharges. Great question, Stephen. So here's the vector multiplet, same philosophy. We want to treat the auxiliary field in sort of a more equitable fashion. We do a duality transformation on it. And sure enough, this is what the vector multiplet looks like in this language before you do the duality transformation. But this is what it looks like after you do the duality transformation. You might say, well, gee, that looks like the chiral multiplet. Yes, it does, but we're going to keep on pushing on. So when you actually do the business that I was telling you, taking the supersymmetrical equations in 4 space, restricting the fields to only depend on time, you will be led to systems of equation that look like the ones I'm showing you on this slide. There could be a bunch of bosonic variables. There'll be a set of fermionic variables, and the D's on the bosons lead to fermions. The D's on the fermions, which are down here, lead to time derivatives of the bosons, because that's what working with the duality, actually, the dual versions actually guarantee. So these equations are very symmetrical looking. In fact, you can write them very concisely, as I'm showing here. The D on the bosons give you fermions, D on the fermions give you time derivatives of bosons. And these coefficients, well, those coefficients come from actually doing the projection. You have to work them out. And you can, later we're going to give some explicit expressions for them. But what you find is that what supersymmetry involves at this level is putting a set of restrictions on these coefficients. You can think of them as coefficient matrices, one associated with each supercharge. That's what the significance of the I index is. The lowercase letters are simply telling us how to swap among the 4 fermions and the 4 bosons to calculate the effect of the supercharges. By the way, we call this the Garden algebra. This is a name that my colleague Michael Fox gave to this collection of conditions. So Michael and I started this in this work in 2005 or so. But very shortly after we concluded, it'd probably be a good idea to get some mathematicians involved, because we were probably going someplace that, you know, physicists don't typically go. And so we gathered a group of mathematicians around, and one of whom is actually on this Zoom. My colleague Kevin Iga, I saw his name as we were starting, so he's actually watching this. So by talking to Charles Duran, Kevin Iga, and Greg Landweber, all mathematicians, some very interesting things start to emerge about these images. Now, we had obtained the images, as I said, by simply projecting to 4 dimensions. But one of the things that mathematicians always do is they look for rigor in mathematical results. And so our mathematical colleagues realized that these figures that we were getting from projection of supersymmetrical equations actually belong to a discussion of cubical cohomology. And I'm going to explain the significance of that in a moment. So suddenly you find yourself starting to think about topological ideas associated with these theories. Let me give you the simplest way to explain how cubical cohomology enters into this game. So what I've drawn here, just like we can draw a cube, a 3-dimensional cube on a 2-plane, you can also draw a 4-dimensional cube, the tesseract on a 2-plane. And one of its renditions looks like this, which is very similar to what's called a Hasse diagram in many applications. So start with the cube. Here we're starting with a 4-dimensional cube. Put a bunch of dots at the vertices, open and closed dots at each end. Why don't we have 2 of the same color? Well, because open dots basically represent bosons, closed dots represent fermions, and these lines between them are the orbits of the generators as they act on the field. So you can't put 2 open dots at, on a link or 2 closed dots. So you first do this all the way around the 4 cube. Next, you color parallel lines the same color. So these 2 lines I'm pointing here and here are pointing in the same direction. So we're going to choose green for them. The lines going here and here are pointing in the same direction. So we're going to put orange there. So you put same color, all parallel lines. And the final rule is that you don't imagine this is a real object. You can grab it by the vertex here, let it hang under the influence of gravity, and it takes the shape that you see over here. This satisfies a condition that no open dot and closed dot is at the same height. And why is that important for physics? Well, remember I told you the open dots represent bosons, the closed dots represent fermions. And if you look back at Lagrangians, the engineering dimension of bosons and Lagrangians is always different from the engineering dimensions of fermions and Lagrangians. And this height assignment in the diagrams corresponds to the engineering dimension back when you're looking at Lagrangians. Now that you know how to build these things, right? Now you don't need physicists to tell you how to get to these objects. You just follow these rules. Start with a hypercube, dress up the nodes, parallel lines get the same color. Oh, I didn't talk about one of the rules. One of the rules is that around every square face, there must be an odd number of dashings. These dashings, by the way, are minus signs. And so if you follow these rules, you can build these kinds of matrices that we call the LNR matrices to as much strength that you have. So later, we realized working jointly, so all 6, 7 of us actually, Robert Miller was one of Chuck Duran's students at the time. We were studying this problem, and we realized that not only was topology entering this, but so were Z2n vector spaces. In other words, the mathematical venue for talking about error correcting codes. That these things have error correcting codes built into them, and you can't stop them. Not because you're trying to put them on a computer, they're part of the structure of the equations. And what's the origin of these error correcting codes? Well, remember I told you that all of these images actually start off as cubes. And if you have an object that's a cube, then you can think of its vertices as being labeled by tuples of the numbers plus or minus 1. You can think about this in the case of the square, right? You can put, if you put a square on a plane, you have one vertex that's plus 1, plus 1, you have minus 1, plus 1, minus 1, minus 1, and minus 1, plus 1. So tuples like this can represent the vertices of any cube. But since minus 1 is equal to minus 1 to the first power, and plus 1 is equal to minus 1 to the 0 power, they're bits. Anything with the topology of cubes necessarily has a bit-like structure associated with it. And since our diagrams can be regarded as coming from cubes, it means they had bits built into them, even though we didn't know it. Here's that same object I showed you a moment ago, but now with its bitwise addresses showing. And the meaning is, if you move along a red link, you change a 0 into a 1. So that's how we get from here to here. You change a 0. If you move along a green link, you change the second bit to a 1 from a 0. If you move along a blue link, we see it's the third bit changing, and along a black link, it's the fourth bit. And you can apply these, knowing these rules, you can actually name everybody else in the diagram. And you get a consistent name no matter the path that you take to get there. So it turns out if you want to get the things that we were finding from physics, they look like this. They don't look like that. And so what we found was that error correcting codes are actually what, this figure could be folded in many ways. Let me see it like that. And in most of those ways, if you convert back to the equations, because remember we get these things from starting from the equations, you'll find that equations that you get for most foldings do not obey the supersymmetry algebra. Only one will, and the one that will is the error correcting code. So the error correcting code somehow knows about supersymmetry and preserves supersymmetry when you take these larger cubes and basically treat them like macrame. What about Lorentz symmetry? Because, you know, you would say, Jim, what happened to all the Lorentz symmetry information that was present when you were at the apex of the pyramid? And I would tell you, I think it's still there. Now, the way that it's still there is something that I settled finally just this year with 2 of my students here at Brown, Hazel Mock and Yangre Hu. What we showed was that these vertices in these diagrams, you have to allow them to carry information. And the information you need to allow them to carry are actually Dinkin labels. And so the Dinkin labels that were there in higher dimension because you knew what the indices were on the field is, if you will assign those Dinkin labels to the vertices, then you actually have information about the Lorentz transformation properties of the fields in 1 dimensions that come from higher dimensions. And furthermore, you not only do that, we use this to solve a problem that had never been solved in 11-dimensional supergravity. Namely, 11-dimensional supergravity is known as an on-shell theory, as I described several minutes ago. No one had ever figured out, well, we knew how many field components there were, but no one had ever figured out what representations of the Lorentz transformation all those field components fall in. And let me go back and talk about this problem in a way that I hope will be accessible. So this, Dinkin is, no, I'm sorry, let me do the vector multiplet, it's better there. So here's the vector multiplet at the top here. These three fields are not independent in terms of Lorentz symmetry. In fact, they're the spatial components of A mu. And so if someone had come along and told me, aha, Jim, what you really need to do is assign a Dinkin label to these things. These things are all associated with a single Dinkin label. Then I would have said, aha, yes, then I know that these three nodes, which by the way, are the three nodes that you see over here, that these three nodes are actually associated with a vector in the 4 dimension, not three scalars. And so using that kind of information, working with Hazel and Yangre, we were able to analyze the 147,483,648 components of bosons and fermions associated with supergravity in 11 dimensions. When you don't imply the equations of motion, we could finally figure out what Lorentz representations are there. And this has never been done before. And Dinkin labels turned out to be the amazing. Once you know about using Dinkin labels, you can actually write codes that are far more efficient. And that's what's in our problem about how we were able to solve this problem no one had ever been able to solve before. So let's look at these L matrices and R matrices a little bit more closely. Well, they all have the following form. You can split them into two, each L can be split into two parts. One part is a purely diagonal matrix that has either plus or minus signs along the diagonal. The other part of the matrix is actually a permutation. And so every L and R that satisfies that supersymmetry Garden relation, which is a condition necessary for supersymmetry in the one-dimensional quantum mechanical theory, has to have this structure. We use some tricks about notational tricks that I won't bother to waste your time with, but we have all kinds of tricks. Here's some explicit forms of those matrices. In fact, the set of L's that I'm showing you here are the ones that corresponds to the chiral multiplet. And you can see the sign factors, the sign prefactors are all written here. And even the trivial sign prefactor, namely the one that's all plus ones. But these parts are permutations. You can tell they're permutations in a couple of different ways. One is to act with some object, object with 4 components. You'll see that these things just shuffle the 4 components around. So these are elements of S4. Now what's interesting is if you now think of these as elements of S4 and you want to get back to preserve supersymmetry, you have to get a sign factor. But what sign factor do you choose? Working the reverse way. Remember, we got this because we started from physics and went down. But if you started from the mathematics view and go up, then what determines these things? Well, we don't have a really great handle on that. We know when it's determined, but we're still exploring what are the rules for determining these things. However, there's another mystery. I and my student Isaac Chappell, together with my physicist colleague, actually studied these things some time ago. And we found that the chiral multiplet was associated with the permutations. The vector multiplet was associated not with the same permutations, but different permutations. And also it was true for the tensor multiplet. So in some sense, the networks keep track of whether something is a chiral, a vector, or a tensor multiplet by saying that they are associated with different permutations in these L matrices. So the information about the multiplet isn't actually lost. You just need to know how to recover it out of the network in which it is embedded. From our mathematician colleagues, however, we knew that we have general rules for constructing these L's and R matrices. And in fact, you can construct 3 additional ones that do not come from projection. They just come from the rules that the mathematicians gave us. And so there are a total of 6 of these things. You can represent this as a pie chart where each of these objects occupies 1/6 of the pie. And that's a picture that we started drawing in this paper. And as a sort of, I hope Kevin doesn't get mad at me for revealing this, but we started calling that the Kevin's Pizza, that pie chart representation of these things. You can also represent permutations in what's called cycle notation. Let me explain that. In this notation, this says the number 1 goes to 1. The number 2 goes to 4. The number 3 goes to 2. And the number 4 goes to 3. So this is one way to represent a permutation. But there's a more efficient way to think about cycles. This notation says 1 goes to 3. The number 1 goes to 3. The number 3 goes to 4. The number 4 goes to 1. And so if you want to know, so 1 goes to 3 is actually this one, if you use this notation. So these are notations, but both represent the same objects. Okay, so, wow, pieces of pizza that break into 6 equal parts. What is that about? Well, 3 years ago when I got here to Brown, I started talking to a mathematician, Carly Clivens, who I saw also was logged on. So, hey, Carly, I'm talking about your stuff now. Carly started asking me questions about, well, Jim, you folks have these structures that are signed permutations. They're Coxeter groups. Carly actually works on Coxeter groups. So she said, what's the precise relationship between what you're finding and classical concepts in Coxeter groups? And I was like, duh, I don't really know. And so Carly and I have been talking about this for the entire 3 years that have transpired, almost 4 now. And this summer, we actually came, I think, really, really close to knowing the answer to the question. So that's where we're going to go next. Oh, what about Hodges duality? Remember when I was up at 4 dimensions, I was showing how I could map between different theories by doing Hodges transformations on fields. Can I see Hodges duality in 1 dimension? The answer turns out to be yes, and it's really quite remarkable. So let me tell you how to read Hodges duality. So first of all, here's Kevin's Pizza, by the way, where the different multiplets are represented by 1/6 of the pie chart. And these lines here are actually duality transformations. But how are they duality? Because remember, in 1 dimension, you don't have an epsilon tensor. So how are you going to find this duality that was there when you were in 4 dimensions, you needed Levi-Civita tensor? And the answer turns out to be remarkably simple. Let me start with the chiral multiplet. The way this notation works, it says the number 1 goes to 3, the number 3 goes to 4, and the number 4 goes to 1. So you read it from left to right. But suppose we read it from right to left. It would then say 4 goes to 3, 3 goes to 1, and 1 goes to 4. Now, is there someplace later that we see a 1 going to a 4? How about this one? And so if you read the cycle notation for the permutations from left to right, and then decide to calculate the inverse transformation by reading in opposite order, that inverse transformation is the Hodges dual representation that you saw up in 4 dimensions. So we even have Hodges duality in this 1-dimensional world where you would think the information is just lost about such things. You just need to know how to recover it. Let's do some 3-dimensional geometry. So I'm going to start with an octahedron. I think I misspelled it here, sorry. So here's an octahedron. And what I want to do is I want to cut out square-faced pyramids from the vertices. And so I just pulled this off of Wikipedia. You know, there's a lot of cute stuff at Wikipedia. You don't have to calculate yourself. It's usually pretty good. So here's a description of one of these square-faced, one of the square faces I'm cutting out of the octahedron. We can say all kinds of things about the relations of the heights and the slant lengths and the edge lengths and what have you, and here it all is. But now I've got the octahedron, which is an object that looks like this. And again, you can just go to Wikipedia. They got all kinds of information. They'll tell you that it has 14 faces, 36 edges, and 24 vertices. 24 vertices. Where have we seen the number 24 today? Well, let's see. There are 6 sets of 4 objects here. That sure looks like a 24 to me. So are these two 24s related to each other? So here's the truncated octahedron. Over the course of the last month, one of my, I'm sorry, let me stop here for doing physics and talk a little bit about mineralogy. Because this is crazy, folks. Remember, I told you it's a crazy idea talk. So the question is, can 4D mineral representations of SUSY be realized in a mineral? Let's see. Well, first of all, there's a class of minerals called phagicites. And phagicites are well known. They've been classified. If you're a mineralogist, you can look these things up. But what's really interesting to me about phagicites is that their unit cell structure looks like this. And there are 24 vertices here. And there are 8 hexagonal faces. I'm sorry, 8 square faces. not 6 square faces and 8 hexagonal faces. But the square faces, there's 6 of them, and 6 times 4 is 24. So could these square faces be somehow related to the things I've been talking about purely from reduction? So we're going to take the so-called Permutahedron, which is a mathematical concept that my student Alex Cianjara has introduced me to about a month ago. We've been looking at it, and we think that that's the connection. Namely, if you're a mathematician, one way to think about the truncated octagon is as a 3-dimensional subspace of a 4-dimensional space defined by the equation that you can see in the middle of the text here. Each of the vertices can, in fact, be identified with the permutations that we saw coming from the L matrices by reducing from 4 dimensions. Here's another Wikipedia picture of that object, chosen a slightly different orientation, but still here. And so Alex found this great film of a mathematician, a French mathematician who was giving an online lecture much like this to a university in India, and he forced me to view it. And at a certain point, I got it. He thought there was something interesting there, but for me, it was like stunning because he kind of forced me to look at it, embarrassed me to look at it. And I finally looked at it, and he and I started talking about it. And then at 5:30 the next morning, I had a conjecture about the structure of the Coxeter group, because sign permutations define Coxeter groups. I had a conjecture about what supersymmetry was doing. So I've come as close as I've ever come to answering Carly's question, and I'm about to explain that. Here's another picture that Alex has drawn, this particular image. Here, the colors that you see, in fact, it was this image that Alex showed me that set my mind afire, and I woke up with this answer in my head, an answer to 300 calculations, which is nice to be able to do that still as I approach age 70. And so it was this diagram that, at least a handwritten version of it, and this particular one was created by Alex. And if you look at this, you might say, well, there's some kind of a symmetry here, and maybe I can't quite make it out. And so what Alex and I started doing was asking questions about, if you take objects that belong to the same quartet, what is the number of steps that it takes in this diagram to get from one such object to another? So if we take, for example, VM3, this is an element of VM3. How many steps does it take to the next closest one element? 1, 2. And you see a 2. How about to the next closest one? The answer is 4, although the next one is 4. 1, 2, 3, 4. How about getting to the farthest one? The answer is 6. So 2, 4, 6 was the answer. It turns out that if you pick any element in any of the quartets and ask the question, what's the least distance to travel to other members of the quartets, you only get the numbers 2, 4, and 6. And so the sum of these numbers is 12. More remarkably, however, if you pick an element from one quartet and calculate its minimal distance to elements of another quartet to which it doesn't belong, the sum of those distances is also 12. It's not the same 2, 4, 6. You can parse the number 12 into a couple of different ways, and it turns out that this minimal distance from an object to members of other quartets is an invariant of this graph. And what's interesting is supersymmetry is actually picking these quartets. And so what's going on is that supersymmetry is picking out a certain kind of an invariant that sits inside of this kind of a graph. And by the way, this is some called weak ordering or Brouhat ordering of the permutation group. Again, a well-studied topic in mathematics. But that's what supersymmetry has launched us into, this very interesting understanding of what supersymmetry wants from Coxeter groups. So that's it. Now, what does this have to do with minerals? Well, let me just show you the Permutahedron one more time. And this time also showing you the supersymmetry quartets. So here's the Permutahedron, and you can see the CM quartet members are here, 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 and here. And if you look at that picture for a moment, you say, well, gee, they're as far away from each other as possible as pairs, and that their axis of orientation, if you think of coming out of the paper as the x-axis, if you think of up and down as the y-axis, and if you think of across, if you think of x and y, x coming out of the paper, y going across, and z going up and down, what you can see is that if you think of a dipole that points from one member of the CM pair to the other, there's some kind of an alignment with dipoles. Now this is just for the CM multiplet. Let's do the other multiplets. Well, here's the tensor multiplet. And again, it's along, this time along the x-axis, and there's this kind of dipole-like alignment between the two parts. In fact, you can run through all the multiplets and you find exactly the same behavior. It is as if this is a physical system. What kind of physical system? And so, since the mathematics of minimal four-dimensional n=1 supermultiplets representations looks a whole lot like the crystalline structure seen in Hodgesite, for physicists it raises a kind of an interesting question. If someone could take the unit cell of one of these Hodgesite minerals and put a charged dipole, put in two charged dipoles, would the lowest energy states for those dipoles, would they in fact be exactly the patterns that we're finding from looking at the group theory of the relativistic supersymmetrical theories? Now, this is probably, I don't know how to do it. I tell people, you don't want me in a lab because I can break equipment faster than the speed of light. So you don't want me to try to run this experiment. But I would really like to, at this point, I'm going to start talking to mineralogists and find out, are there some unusual properties of Hodgesites that might have some kind of relationship to realizing these supersymmetrical representations in terms of free space in a crystal? Now, of course, it's unlikely, but stranger things have happened in this universe that where Wigner has said mathematics is unusually effective. So this is the end of my talk. I'll take questions now, and thank you for listening.